This lesson will give you the necessary notes to do the homework that is titled Limits by Graphs. All right, let's jump right in. Here we go. Let's start by understanding the terminology that's written here. When we see this sentence right here, we're going to read the limit as x approaches c of f of x is L. Okay, so let's see what this means on each of these. What we're looking at here is here's C, and as x approaches c, and we're going to actually look at it from both directions, as x approaches c, what y value are we hitting? And we can see that that number is L, so that's why that equals L. Same thing happens here. As x approaches c from both sides, even though there's a dot down here, the number that it's approaching is L. And lastly, even though there's no value here, we actually have a limit because on both sides we are approaching the number L. All right, so what happens when a limit doesn't exist? So a limit does not exist when, if I'm approaching it from the left and approaching it from the right, I get two different numbers. Here I got 1 and up here I got 3. And so if it does not exist, we simply say it does not exist. But there is something we can do for those situations. If we don't have an overall limit, we might actually just look at the left or right side. So let's start with this one. This would be the limit as x approaches c from the right. Let's just write that. Left. As x approaches c from the left. And then we've got a more technical definition here, which says that if we make values for f of x as close as we want to L by making x sufficiently close to c with x less than c. All this is saying is that we're coming in to c with x values that are less than c, and we're going to get a number very close to the limit. Now, if we can come in from the left, we can also come in from the right. So that's our next one here. We can say that x approaches c from the right. And again, in this statement, we're saying that we're picking x values greater than c, and if we pick close enough to c, we're going to find the values that get close to L. All right, so let's try this out. So here was the graph where we said that the limit did not exist, but when we came in from the left, that's coming in this way, we approached a value of 1. So we would say the limit is 1, even though no value exists there. When we come in from the right, we're getting closer and closer to a value of 3. So we would say that the limit is 3. But because 1 and 3 are different numbers, we would say the limit as x approaches 2 does not actually exist. All right, so here's our definition. The limit as x approaches c equals L if and only if the limit from the left, right down here, equals L, and the limit from the right also equals L, which basically says that our limit has to be the same on the right and left for our overall limit to exist. All right, so we're going to try a bunch of problems here. So in this first one, we are interested in what happens as x approaches -4. So we've got this whole graph, but all we really care about is when we're close to -4. So let's just mark that one right here. This is the region we're talking about when we're considering this graph. And here is, oops, I need a blue pen. Here is -4 right there. Okay, so what is the limit as we approach from the left? We're coming in this way, and we want the y value, which is going to be 2. What's our limit as we come in from the right? Oh, we're approaching the same y value of 2. So that's 2. I see that my limit from the left and right are the same, therefore my limit as I approach -4 is 2. But if I put in, this is supposed to be f of -4, if I put in -4, I get this point right here, which is up here at 2, 3, 4, 5. So even though the value is 5, the limit is 2, because as I come in on the segment from the left and right, I'm actually approaching the number 2. All right, let's try another one. Let's see, this time we're looking as we approach 2. So let's see, that's kind of this region and this region. So as we approach 2, here's our x coordinate of 2. All right, so first I'm going to approach from the left. Well, there's nothing on the left here, so I'm going to be down here as I approach from the left, and I can see that I'm going to hit a y value of 1. As I approach from the right, I'm going to hit this y value of 5. I can see that the left and right limits are different, so does not exist is my answer here. But for f of 2, I look to see if I have a closed circle. Well, this is an open circle, so that's not my answer, but I jump up here, and oh yeah, if I plug in 2, my answer is 5. Now, if you think you've got the hang of this, I would encourage you to pause here and try this one out before I go over it. All right, welcome back. This time we're looking at what happens at 5. So 2, 3, 4, 5. Here it is. We're in this region right here. So for 5, there we are. And we start with the limit from the left. As I come in the left, I think that's at 4. 1, 2, 3, 4. Yep, I'm at a height of 4. As I come in from the right, same. That's going to be 4. The left and right limits are the same, so this is 4. F of 5 is an open circle, though, so f of 5 actually does not exist. All right, let's try another one. Again, I encourage you to pause before I go over this. All right, this time we're approaching 0, so this is our region right here. And let's take a look at what happens as I approach 0 from the left. So from the left, there we go. I'm approaching, this is at a height of 3, so that's going to be 3. As I approach from the right, I'm also approaching 3. Those are the same, so my limit as x approaches 0 is 3. And f of 0 is this point right here. That is also 3. And that's a very special case. When all of these numbers, all 4 of these are the same, that actually is going to relate to our definition for being continuous. So let's look at that definition on our next slide. So it says here, now we can offer a more formal definition of continuity. And we are going to say that a function is continuous if the limit from the left equals the limit from the right equals the actual value of c. So our function is continuous any place where the limit is the same, the limit from the left equals the limit from the right equals the actual value. So if we were to highlight places where this is continuous, we could highlight this section along here. We would highlight this section along here. All of this is continuous. This is continuous, and that's continuous. All right, good luck on your homework on limits by graphs.